So here we are, back again. And today, or in this video rather, we are going to explore the LAG computer architecture. It's going to be a lot of fun. And yes, the first level we are going to play is the XOR level. Let's go. Using the instructions of your computer, read the input twice and XOR the value, XOR the two values together. Interesting. So we're going to have to program a XOR gate instead of actually implementing one in on the hardware level. We're going to have to find a software solution for this. Interesting. So what we can do is basically, once again, have a look at De Morgan's law. De Morgan's law. And wait a second. We're gonna have a look at the instructions. Do we already have a XOR or something that is similar to XOR? Compute. We already, by the way, we could implement a hardware solution. So we would just, since we have unset bits in our compute section, right? And by the way, I don't know if you understand this, but you are also, like, you would already be able to define instructions. Like, you don't have to solve this game from this point onward, at least, exactly the way that I'm doing it. You're quite free, and you can actually already define your own instructions and stuff like that. So we can subtract, add, we can AND, we can NOR, we can NAND, or maybe we can do both variants. Anyway, we cannot have a look at De Morgan's law in this case, but what we actually can do is see, there should be a XOR level, and we have a level search, so look at CF. Yeah, here's the XOR gate. It is composed of 4 NAND gates. Maybe we can actually take a screenshot and might not even need it. So we'd have to NAND 4 times. NAND. 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 Then we would use, we go R3 to out. We already know this because, you know, into R1, into R2. Now I'm actually gonna have a look at the screenshot. Wait a second. If we want an exclusive OR, yes, I'm gonna have a look at the screenshot. It's gonna be so much easier than just solving this using logic. Using only logic. First of all, we NAND both of them together. Right? And then we move R3. By the way, there is our screenshot. We're just implementing this whole thing in code. And both inputs. Which is basically creating this output here, right? Which is then saved into R4. Next thing we would do is we would put input 1 into, well, first of all, we are going to put input 2 into a register where we can basically save it. Input 2 is sitting in, so we don't lose it when we NAND again, right? Into register. That is unused. And then we would implement this part. Take the output, which is sitting in R4, put it to R2, which is this output. We put it into the second register, and then we want NAND again. We're going to have to implement these later. So now we have another value that we need to save, which is basically this right here, right? We're going to move it to R0. Now, since R2 is basically still occupied by this value right here, we're going to take the value of the first input, of the second input that we saved into register 5, and put it, in this case, into a register 1. NAND them together again. Now we have these two values, right? This value, like this value, is sitting in register 0. So we're going to move register 0 to register 1. And this value is sitting in register 3 right now, which we wouldn't even have to use this value, save this value. This is not necessary anymore because we don't need it anymore. We would take the value that is sitting in register 3, which is this output, and since 1 is already occupied, we put it into register 2. NAND them together, and now this will solve the level. R4 to R2. First of all, go into copy mode. No, instructions. This right here is copy. R4, which is this one. First is the input, second is the output. We remember this. R4 to R2. We're going to, for the sake of completion, maybe do all of them, or maybe not actually. Since we're going to build the lag architecture next. To 5, right? This is 5. should solve this should solve the level. And for the sake of cleanliness, we add a loop. Even though we probably don't need it. Doesn't make a difference. Oh well, it does. It creates 2 more lines of code. Outreach out. Okay, this is wrong. Why is this wrong? I don't see why this would be wrong. We've built it exactly the way we were supposed to. Okay, let's have a look again. I'm gonna bring in the screenshot again. We're going to debug this. Let's make this a little bit smaller. We need it to be this big. We're going to step by it, step through it, one step at a time. First of all, we're going to take our input and save it into, save it into register 1. This is our first input, right? This is correct. This is doing this basically, sitting here. Next, we're going to take our second input, save it into register 2. There it is. It's correct as well. So the next thing we're going to do is we NAND them together. Sorry. So we just NANDed them together. Is this the correct solution? We will figure this out later. It doesn't matter for now. So now we have our value, which we put into register 4, right? It is this value. Here we go. Next, we're going to take R2 and move to register 5. So we're basically saving this value because we're going to need it later. And now it is sitting here. So the next thing we're going to do is we take this value, which we created when we NANDed them, right here, and saved into register 4, and put it back into register 2, which is this one. And then we NAND these two together again, which creates this number, 91, apparently. Then we move R3 to R0 because we want to save this value into a register where we can later reuse it. Just happened. Now we are going to take the value in register 5, which is once again this value, and put it into register 1, right? Because the next thing we were about to do, or we want to do, is we take this value, which is this, and this value, which is sitting in register 5. We saved it earlier. NAND them together. Okay, now there's the problem. Register 5 is not sitting. I guess then there's the error on this line. Maybe this is wrongly defined. Let's see. R5 to R1. It is wrongly defined. This is not R5 to R1. This is R4. Oh wait. R5 to R4. This is R5 to R1. Save it. So now this saves the level. Zor. Type is architecture. Nice. Byte Zor. Interesting. Now we're going to implement it on the byte level. Can you just as the previous ones, now we're going to create a hardware solution that would solve the level. And I guess we're going to be asked to basically build a advanced version of our ALU for the lag architecture that uses or utilizes these components later. So here we are. This level is basically once more a level like the previous ones where we just build a I don't know why this bigger component just by adding a bunch of small components. Zor and XNOR. Interesting. Thankfully we don't have to use the I have to manually build the XNOR gate by hand. Yeah. And just as the custom components, these components are a lot like, yeah, they are really reusable. And yeah. Just as I said, we could have already used the custom component to solve this level, and then just use the custom component to finish the byte Zor, which would have been a cool variant to play the game, I feel like. Anyways, create a circuit that always outputs the number 164. So this one is quite. So these two, we don't even need multiples. These two create the number 160, and we're supposed to output 164. Here we are, 164. Level complete. Byte constant component. Next level, we're going to check for equality. Output green when both inputs are the same, which we can do by using a Zor gate. Now I actually wish I would have built the the custom XOR, because we could have used it in this level as well. But we don't have to use the XOR gate, because if we not one of these, right? No, in this case we would actually have to check for zeroness, which we can do by using our ALU actually. Oh, we're not allowed to use custom components, which makes a lot of sense, because we haven't unlocked this so far. Later in the game we will unlock something that is called the NAND score, and the NAND score basically determines how many NAND gates your architecture and your build uses to create a score out of it. And using the ALU would skyrocket the NAND score, because it accumulates throughout the components, right? Because every component is composed of lower level components, the NAND gates add up. Using the ALU in one level would, since it basically creates an immense NAND score just by itself, skyrocket recursively. So what we are going to do is if there's an exclusive OR in any one of them, that would mean they are not equal. That should be correct, right? Oops. Top side is taking the first. What is this? I'm sorry, I drank quite a lot of coffee today. I'm a little bit in the mood, I guess you could say. Do you know this feeling when you drink too much coffee? When you drink like 4 cups of coffee and you feel like, oh, maybe it's been a little bit much. I do. No, let's go like this. It's gonna look nicer. Maybe let's do it like this. So yeah, because if there's an exclusive OR in either one of these things, that would mean they are not equal. Okay, wait, doesn't this work? There's an exclusive OR. Oh, because these are supposed to be ors and not zors. Yep, now it solves it. Great. Unsigned less, signed less. Yeah, we are going to explore these two levels in the next video. I hope you had fun up to this point, and I'm excited to play the other levels with you. Goodbye.